The star is coming.
Did you hear me?
Yeah. Oh, I didn't hear that yet.
Now we're gonna do it as a lot. So to us.
She's coming. Yeah, she's coming.
Cool. Hey, good evening, everyone. Today we'll finish up related rates and get any of your questions on any, could be on any of the problems. And then Monday also additional day for review. Do you have any questions? Should we start? Claire?
Go over number 7 from 3.6.
You bet. 4.6. Logs. Number 7, you're the best. Log base 10. So I'm gonna start out by writing it down. Log base 10 of x cubed plus 1. Claire, did you know we could write this as log base 10 x cubed plus 1 over log base 10 of 10.
Can you do that with any, like if
Isn't that
it's
cool?
log base 5
Yep. You absolutely cool. And cool. It's a property of logs. It's a change of base. You can call it the change of base formula if you want. Because some like we wrote it in another format. But what I just wrote, that's not gonna help. So I'm gonna cross it out. It's the next way we want. So you can write it as a ratio of logs. I'm gonna go like this. I don't want that. This is what we want. We can write it like this. We can write it in terms of ln as long as we write ln of x cubed plus 1 divided by natural log of whatever that base is. So I know this was base 10, that's the common log, but it could have been base 6 or something.
Yeah, there's one that's 5.
Oh, see, there you go. We were writing ln of blah, 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 divided by natural log of 5. So you'll notice, we're like, oh my goodness, this is really 1 over the natural log of 10. The natural log of 10 is just some irrational number like pi. So that's just a constant. I'll just keep that in front. That's like a big constant right there. Times this is equal to that times the natural log of x cubed plus 1. So when we differentiate this, as long as we fix that at the beginning, Claire, then when we do the derivative, we'll just do our derivative of natural log, and we'll just keep this constant in front by the constant rule. Isn't that cool? And you can do all LOG base 10s and LOG base 5s that you want to when it comes to differentiation. So I'll leave this, I'll just carry this down. All right, now we're going to differentiate this. So the constant rule says, oh, I can just keep that constant there. Now, how do you differentiate that?
2x squared over x.
Oh, I love it. this x cubed plus 1 just goes down here, right? Good. So it's like this. I don't know if you're curious. When it comes to this, so it makes sense. We're doing chain rule. The derivative of natural log of x is 1 over x. So when I do chain rule, I'm calling that g. Right? So I go 1 over g times g prime. And then g prime is, I'll just take off the 1, what's the derivative of x cubed plus 1? So isn't that cool when you do derivative of an ln? The natural log actually disappears. And there's the answer. You can leave it like this, or if you want, you just want to write it as 3x squared over natural log 10 times x cubed plus 1, but that's it. There's not many of those though, are there? And just expect that. Just expect that, seriously, throughout the calculus go. You may never see it again. We'll see. I'm going to check with you after Calc 3 and differential equations. If you ever got a log base 10 over, usually it's natural log. Wasn't it similar to this, everyone? We rarely got this guy. Wasn't it similar? And we said, oh, the derivative was 2 to the x times the natural log of 2. Or here's another one. 10 to the x. We rarely get these. You go, well, what is the derivative? Natural log of 10 times 10. We just rarely get those. So here, I guess we're just multiplying the natural log of that number, where it's the base of the exponent. And with these logarithms, we're dividing by the natural log of the base, if that helps. But they rarely come up. You'll see how many times you get them through the feature sections. It's usually base, you know, natural e, the natural base e, where you get natural log. Hey, any other questions? Going on?
Yeah, on 3.7, actually, we were doing it that day. Number one, like when the particle, when the particle is speeding up and slowing down, we did two curves. You were showing about the magnitude of V. Can you go over it for one more time?
I sure will. And you're talking about doing the speed, right?
Mm-hmm.
Let's do it. And when it comes to speed, there's a couple ways to look at speed. I think the easiest is to think of how that's the magnitude of velocity. And like we could put the absolute value bars around velocity. And just think of that graph all upstairs. So if velocity went like what? Let me just make a velocity. No, when I say the velocity went like this. Let's say that was velocity. What would the speed graph do? Speed would go, and then what would happen to all this? It'd flip right up, and that, like that. Does everyone see that? And so when they go, find where it's slowing down or speeding up, we can just go speeding up, slowing down, speeding up, slowing down, speeding up.
Slowing down.
I know, and that's the way I think, great way to approach speed.
Long time ago, I mean, like over 20 years ago, we did it in a way I just don't remember. Like you do both velocity and acceleration, and there was something like both, if they were both positive, I don't remember what the formula was.
You got it. You know? If
Both were-
velocity and acceleration are both the same sign,
Same sign, yeah, same sign. Then they're speeding
what's
up.
happening with the object?
Speeding up, yeah.
It's speeding up. So if anybody wanted to know this, Art, you are correct. People like this little physics thing. If velocity and acceleration are both positive, the object or the particle is speeding up. But if they're both negative, the object's also what? Speeding up.
Yeah.
Velocity and acceleration have different signs. One's positive, the other one's negative. Velocity's positive, acceleration's negative. Velocity's negative, acceleration's positive. What's going on with that particle?
Speeding down, yeah.
Yep, slowing down. That is absolutely true. You can actually use that to, analyze it and solve that problem.
Yeah.
That's a great little fact to know, though.
Isn't that used for the second derivative tests?
That's right. You're right. Concave up, concave down. Very good.
So when is it slowing down?
Oh, when's it slowing down? So this is, and we're talking about velocity and acceleration. Let's say we're talking about some particle. If both velocity and acceleration have the same signs, that means they're both positive, or they're both negative at some point, at some time, it could be, just for, I'm thinking like at time equal to 2.3 seconds, they're both positive. That means the object has to be speeding up at that moment. And then we go, all right, when's it slowing down? When velocity and acceleration at a moment in time have different signs. What I mean by that is one is positive, the other is negative, or vice versa. Cool.
Couldn't you also look at it like it's going closer to the x-axis, it's getting slower, and if it's moving away, it's getting...
Brilliant, I love that. That's good, I like that. So you can look at all these ways. Everyone, please use the way you find the easiest. I love just looking at the speed graph. You know, like, all right, I'm just gonna go, all right. Object sped up, object slow down, object sped up, object slow down. And this is just to find it. It's always just what?
Absolute
Absolute value. Everybody know where abs is on the calculator? I use catalog. So if you go to second zero, look at the first thing on the list. If you ever just wanted to graph the absolute value of any graph,
It's also if you go math and then over to number.
oh, you're the best. Because you can also find it in math, arrow to the right to none. The ABS.
And then it's the first one.
That's the first one on the list. Outstanding. That's what we did it. I used to teach AP Calc years and years and years. Students would crush that exam, you know, but whenever that's what I always recommend. But everyone, you know, they would use this technique, what you mentioned about going closer to the x-axis, but this always would work.
Which one is that? What is the one he said? Closer to x-axis?
As he was saying, he realized when it was getting closer to that x-axis, like the velocity, like right here, right, versus the velocity right here, what would that indicate?
Slowing down.
Going slower.
Yeah, but then it starts getting what? Further away, yep. Exactly. Any others? Hey, we'll do some related rates problems. We can do any you want. You do ones from the text. The one I want to do was an even problem, because the even answer's on the back, right? And so it's number, maybe you got a chance to do it, I don't know. It's number 14. It had ships moving. Is there another ship movement problem?
21.
Look at the examples of the book. Example 1, example 2. Nah, example 4 is a car. All right, let's do 14. Hey, before I erase this, I should show a student in here. If you're like, he said something about speeding up and slowing down with the signs, and I didn't understand what it meant. I guess maybe before I erase this. And right there, at that moment in time, this is time. Do you agree the velocity is negative?
Mm-hmm.
Right? Okay. And isn't acceleration derivative of velocity?
Mm-hmm.
Okay, so if I took the derivative velocity, I'm talking about the slope here. So that point right there is negative. Right there, so I'm going to say v is negative. Acceleration is the derivative velocity, which is slope of tangent line. And when tell me about the slope of that line. Is the slope of that line positive or negative?
Negative.
So acceleration is negative.
So speeding up.
And so when velocity and acceleration have the same signs, that means the object must be speeding up at that moment in time. And you would see it right here in this graph because the object's doing what? Speeding up. Right there at that moment. Does that make sense? I thought before I erase this, I wanted just to show you that so you're like, hey, how can you look at that? That's exactly how you can look at it. It's how you can analyze that if you like that. I'm working a problem. You don't want to do this. Right? All right. I'll read this to you. Let's make a decent sketch. At noon, ship A is 150 kilometers west of ship B. Okay, first one. West coast, right? East coast, we're gonna get this right. That's west. That's east, right?
Mm-hmm.
And they go, at noon, ship A is 150 kilometers west of ship B. All right? A, I'm gonna put it in the middle. that do? What do y'all think? At noon, ship A is 150 kilometers west of ship B. Will that do? For a sketch? Good. We drew something after we read that, right? But now these ships are gonna move somewhere. They might go north, south, we'll see. They might go this way, they might go that way, east or west. Here's what they said. Ship A is sailing east at 35 kilometers per hour. All right, let's just make a note about the other one. This guy right here, he's going that way at 35 kilometers per hour. Ship A. What about ship B? Ship B is sailing north at 25 kilometers per hour. Okay, you're going that way. 25 kilometers. It's all about pictures, right? So far, so good? Hey, what time was this again? When did this happen?
12 o'clock.
You're the best. It was the very first statement. Sometimes we'll forget about it. The problem is you can get all confusing. You're awesome. You said this was at noon. So this was noon time, right here. This is the picture. And then they move. And then here's the question. How fast is the distance between the ships changing at 4 p.m.? So we need to change our picture.
So after
And
4
then we'll
hours.
never look at this again. Right? What's going on at 4 p.m.? So let's just do it per hour, right? After 1 hour, how did B move?
25 miles.
25.
25, yeah.
Right, 125 kilometers. At 1 p.m. Where did this guy move?
35.
35. Right? But that's at 1 p.m. We gotta get to what?
4.
All right, so I think we could jump to it. Let's start with B. Where will B be at 4 p.m.?
100 kilometers from.
Oh, look, 25 kilometers, 25 kilometers, 25 kilometers, 25 kilometers. It'll be 100 kilometers north of this location, right? So I'm gonna do that. I'm just gonna extend this thing up. All right, way up here. There, that's good enough. All right, this is 4 p.m. There we are, and this distance right here is what?
100 kilometers
100 kilometers is that length.
from. Yeah.
Now let's move letter A. And I don't know, you're gonna have to help me out with this. Is A gonna stay on this side, or is A gonna get to that side?
No, 140. 35 times 2 is 70 times 2, 40.
35, 35, 35, 35?
140.
140? Because sometimes in these shift problems, anybody in here ever use WebAssign? They'll take this problem, she knows this, and they'll make like 8 random problems like this. And, you know, I get a lot of emails from students. Well, sometimes it depends on the number they choose here. If they, let's say they always use 150. Sometimes ship A will get what? Over to here, true? But sometimes it stays on this side of this what? Vertical line. Either way, aren't we still gonna have a right triangle somewhere? Good. So I just wanna point that out. But if it went 140, 35, 35, 35, 35, then I don't care about this anymore. You're saying right now it's what? 10 kilometers for that distance right there, right? There we go. That's my image. And the question was, let me read it to you. How fast is the distance between the ships? Here it is. Here's A, here's B. Here's the image we want. That original image we had before, gone. So far, so good? Now I want you to tell me something. See this length here? Is this length increasing or decreasing? in that
Decreasing.
right triangle? Because we're about to apply Pythagorean theorem and then differentiate it. So we got to think about the sides of the right triangle. That length is decreasing. Excellent. So we're going to make the rate what? Negative?
Negative, yep.
When we do the math formula. Does that make sense?
Mm-hmm.
Good. Go ahead.
Explain why it's decreasing.
Oh, you saw how, like, maybe I should draw a couple images. First it was like this, and here's A, and here's B. Right? Remember after 1 hour, this went 35 this way, this went 25. Then, an hour later, this what? What happened to this distance? Did it shrink a little bit? Right, that distance, right, and then B what? This length's increasing, but this length is what? Decreasing. Do you see that? So at that moment, at that exact moment, 4 p.m., we can see the length of that right triangle there, that length is actually decreasing. But what's interesting, I hope you follow this, what's going on an hour later? Even though we didn't have to do this at 5 p.m., everyone, but what the heck's going on at 5 p.m.? This thing is now 100 and what?
40.
25 for that one? Does everyone agree?
Which one is 125?
When is going by 25s?
Okay,
This one's going 25.
Oh, at
25.
5 p.m. Okay.
Yep,
Oh,
at
got
5 p.m., even though we don't have to do it. So that'd be 125, it's still increasing. But then this ship would have been where? Over here, how far if it went 35
it.
kilometers?
25.
25, oh, I gotcha. And that would have been 25 over here. But we got a totally different right triangle now. Look at this right triangle. And what's going on with that distance?
Increasing.
Isn't that increasing?
Mm-hmm.
So do you follow me? It depends on the time and the moment. But we can see in this one, okay, at that moment, that length of that right triangle was shrinking. It was decreasing at that exact moment. An hour later, you got a picture like this, and this distance is actually increasing. Cool. So, but because it's decreasing, when I do my math formula, everyone, see that 35? In my math formula, I am gonna put that rate. Do you follow me? Does everyone see that? That's the only thing tough about related rates, is when we look at an image, whether it's a sphere or a circle, triangle, in this case, right triangle, and we're looking at that shape, we're talking about each length. Is the length decreasing or increasing? So when we do the math formula, we can say it's a positive or negative rate, because it is rate of change.
If you put that as point of origin, then in that way it becomes much more, because that's the negative x, you're coming from negative
That's
x,
good.
right?
I like that. Make that the the actual origin.
Yeah.
0, 0, right there. And you go, yeah, that's decreasing. That's negative. Or like he said, it's on that side. All right, everyone. So I am going to make sure that I'm going to call this side right here, not its length negative. That's not negative 10. That's still positive 10. But the rate of change of this side will be negative 35. So what did I go there? Cool. And you also note if it was 5 p.m., this rate would have been positive here. This rate is still positive. Cool. All right, so we're going to set this thing up in a second. Let me see if we got everything. Do you want to use A, B, and C? Will that work?
Yeah, that's cool.
But these are capital A's and B's, so I'll use lowercase a and A, B, and C to represent the lengths of the sides. So, right here, everyone, what is the length of that side right there?
10.
A is 10, right? 10 kilometers. Not 10 kilometers per hour, A is 10 kilometers. What's B equal to?
100.
100 kilometers. I am now stuck. They didn't give me the length of C. What theorem?
Pythagoras.
Pythagoras. And we talked about common right triangle lengths. I don't think this is one of them. You know, I don't think this is a 3, 4, 5 or a 5, 12, 13. You know, you have to really do Pythagoras there. Okay. What's 10 squared plus 100 squared?
100.5.
Take the square root of this. That's a 1, 0, 0, 0, 0, and then I add 100. Square root of 10,100? Is that what it is?
Mm-hmm.
I'm gonna write it like that, because I imagine it's irrational, huh? Yeah. All right, so I'm gonna write it. This is the square root of 1, 0, 1, 0, 0. I'll just leave it like that.
It's 100.5. That's
Was it exact?
no 100.4 irrational.
It's irrational. And everyone, it's irrational, so I'm gonna leave it like that.
Okay.
I love it. Hey, it is 100.5. I'm glad you did that, just to give us an idea what this number is. I'm gonna leave it irrational just so that we'll stay consistent. Any math problem we solve, we won't round to the final what? Final answer, right? I worry someone puts 100.5 on and they divide something and it gets that accumulated round off here. All right. B is 100. Little a is 10. What is dB dt again? How fast was that side increasing? They gave us that rate. 25 kilometers per hour, right?
Uh-huh.
And everyone, do you agree it's positive?
Yeah.
That length's increasing. What's dA dt? This.
Negative 35.
Someone see that? And do you know why I'm making it negative, Amber? That's
Yeah.
gonna be dA dt.
Yeah.
Oh yeah, it's shrinking. At that moment, at 4 o'clock. Most of my WebAssign emails that I receive will be on that concept. The student did everything right, but was using positive 35 in their math, wasn't getting the answer in the web assignment. You know, I've done this 10 times, and I keep getting it wrong. I'm usually like, I bet you that's it. Let's use the problem. It's not their sketch. They make a great sketch. All right, I'm gonna start out with diagram theorem. A squared plus b squared equals c squared. Differentiate both sides with respect to t, right?
Mm-hmm.
2a, d dt. 2b, db dt. 2c, dc dt. We differentiate everything with respect to time. Cool? Now, want to take those 2's out? What I mean is divided 2 on both sides?
Mm-hmm.
Okay. Got an a times a d dt. Got a b times a db dt. C times a dc dt. All right. You're 10. You're negative 35 kilometers per hour. You're 100. You're 25 kilometers per hour. You're the square root of 10,100. And you're x. So what is negative 350 plus 2,500?
$21.50.
And then what's 2150 divided by? And now we'll approximate the answer.
21.39.
29? I'll go to one decimal place. What would that be? 21 point?
40.
All right, I'm gonna squiggle, everyone. 21.4, what's my units?
Kilometers
Kilometers per hour.
Kilometers per hour. Yeah. You probably need 20 of these after this. Don't have to be ships, it can be trains, it can be planes. There's a problem with the plane if you want to do it. Have you noticed that when there's a lot of right triangle problems in here? Not all of them. We did a cone, we did a sphere, we did a circle, but a lot of them are. Hey, can we do one off the practice set? Anybody need a copy of this? They're just additional problems when you've expired, you've done every problem out of the text that we talked about. And you just want extra ones? But I saw there was a related rate problem, everyone, on number 22. But I like it because it's multiple choice. You know, you're like, ooh, I gotta figure out which answer it is. Anybody need a copy?
Yeah, so after you got the 2150, then what did you get?
Oh, so this was, I'm sorry. So this was 2150 equaled this number times dCdt.
Oh, because
And then
that
I
was
just divided it.
Okay, because C is the 101 or 100.5.
Yeah. And Amber, the only reason I didn't make it a decimal, I was like, okay, it's irrational, so I would have had to
just
write.
left it as a square root. Okay.
Yeah.
Okay.
Hey, if you wanted to, Amber, you could have left your answer like this. 2150 divided by the square root of 2. Just sounds better when we talk about the actual ship. Anybody need one? All right, what do we got here? A railroad track and a road crosses at right angles. An observer stands still on the road 70 meters south of the crossing and watches an eastbound train traveling at 60 meters per second. Do you need a copy? Okay.
Yeah.
Amber? Straw's got one. Amber, do you need one?
No, I haven't.
Oh, you got one? Good.
Yeah.
You want one? I wanted 22. They're just additional practice problems. All right. Well, let's make a sketch of this. Observer, stand still, 7 meters south of a crossing. Let's just put a person here. There we go. 70 meters south of some crossing. And at that crossing, watches an eastbound train traveling at 60 meters per second. All right, there goes the train. Eastbound, right? It's going east. And that length's increasing, isn't it? All right. Am I okay if I call that A? You're right. This side's B, and dBdt I already can call 60, what are the units? Meters per second. At how many meters per second is the train moving away from the observer 4 seconds after it passes here? So we're gonna go 1,000, 2,000, 3,000, 4,000, 4 seconds. Then we gotta talk about how fast is the train moving away from this person. And we got another right triangle, right? Cool. So that's 70, but I want, if it's 4 seconds later, that's every second. Isn't this side pretty long?
Yeah, 240.
60 meters after 1 second. Another 60 meters. Another 60 meters. And another 60 meters. I mean, it's not drawn to scale, but it gives us an idea. This is pretty long compared to that 70. All right. So how long is B now?
240.
Is that okay with that? Yeah, cool. Yeah. 4 times that's 60. What were some common right triangle lengths? 3, 4, 5. What were some others? 5, 12, 13, 8, 15, 17. And when I stole that problem from an old AP exam. Anybody know this triangle? 7, 24, and what?
25.
7, 24, 25. So you can tell the examiner, oh, 70, 240. If I'm lazy, I don't want to do Pythagorean theorem. How long would this side be?
250.
250. But if you didn't know these common right triangle lengths, that's okay. Do Pythagorean theorem, right? I'm going to put it down right now. C is 250. I've got this rate. The question says, at how many meters per second is the train? And here's the train. All right. Choo-choo. Here's the train. How fast is that train moving away from the observer? So I am looking for dCdt then. If I'm trying to find how fast the train moving away from the observer. It's increasing. B's increasing. Any observations about A?
Same.
Oh, you are good. See? Here's an image, totally different from the ships. The distance A is never changing in this problem. It's always 70. So what's dAdt?
0.
Let's write it. Before we forget, dAdt, 0. It never changes. Constant. 70 meters always. That's the secret. Then we just A squared plus B squared C squared 2A and dAdt.
And dBdt is 60.
Good job, and it's positive, isn't it?
Mm-hmm.
Because that you can tell that side's increasing, right? Amber, you okay if I knock the 2's out?
Yeah.
All right. How about? Divide them out on both sides. 70. 0. 240. 60. 250. dCdt. Amber, how would you solve that?
You have to divide by 250.
70 times 0 is 0, right? Let's see what you get. What's 240 times 60 divide 250? I can tell everyone by that ratio it's a little less than 60.
57.6.
57.6. Is it exact though? Do I have to do this quick or was it exact?
It's exact.
Huh? Equal.
Meter per second.
Meters per second, thank you. Very good. So the letter answer is A. Good job. These are related rate questions. Don't worry, on Monday you might make me do related rates. Remember what? Reviewing, right? As I'm glancing at this is like I always like to give you just some practice problems. I glance at 17. Anybody know what technique I'd have to use?
Which number?
17. Just to examine it. We might even don't have to work it out, but just to look at it and go, what would I have to do? Something we've learned in the past 2 weeks.
differentiation.
Go Raj, excellent. He's looking at the equation, he goes, implicit differentiation. The y was not what, by itself? Do y'all see that? So if we gotta get a slope, that's derivative, we get dy dx, and we're like, but the y wasn't in the middle. I mean, excuse me, the y wasn't isolated, we'd have to do implicit differentiation. Good.
Oh, you're talking about this one.
Yeah, number 17.
I was thinking about the book.
Oh, let me look at 17 in the book. Oh, that sounds like 14. Man starts walking. Cool. Did you want to do another cone problem?
Yeah.
Okay. Because 27 from the textbook was another cone problem. I don't know if I have a cone one on this practice sheet. I'll look. Oh, good, I do. Number 24. Let's do the textbook first. And if you want to do the cone, do 24 from the sheet, you can do that as well. That's cones. There's something we had to do at the beginning of a cone problem. We had to look at the ratio of radius to height. So what's going on when this is number 27? Gravel's getting dumped. Now the cone's like this. I'm thinking of that. Yesterday we did these. I don't know if I gave you copies.
I have one.
Oh, you did?
Thank you for
doing that. I couldn't remember. All right, what do they say about this cone? This is 27 from the text. Page 249. What do they got? Gravel's being dumped from a conveyor belt at a rate of 30 cubic feet per minute. Here, let's just go like this. 30 cubic feet per minute. Isn't that volume?
Mm-hmm.
That's rate of change of volume. Can we call that dVdt? Yeah, good. That's good. That's dVdt. That's rate of change of volume. It's coming into the cone. It's being dumped from it, so it's positive. It's increasing. This pile's getting bigger. So the volume's getting bigger. So we can write, this is dVdt. You better when it's just coming in here. Right from a conveyor belt. Just dropping off all that cylinder. It forms a pile in the shape of a cone whose, listen to this, base, diameter, and height are always equal.
So that's the diameter equals to height.
We always want to look at this ratio here, right? But we're saying this distance right here will equal
To the height.
this distance. So let me start out with D will always equal H, where D is diameter of that circle. So far so good?
Mm-hmm.
But I eventually want to get to this. So what is diameter in terms of radius?
Half.
So diameter is equal to
Half,
2 radii.
mhm,
So I can substitute 2r for d.
yep,
2 times radius is d. All right, so I'm going to put 2r equals h. Is everyone okay with that?
yeah.
2 times radius is diameter, okay. Now, what is this ratio? This is what we always want to look at before we start a volume problem. What's the ratio of radius to height in the problem they use?
So the ratio,
R over H is 2 over 1 or 1 over 2? Is it 1 over 2?
Uh-huh.
Everyone okay with that? You want to see what I did, Amber?
oh, you
My goal was to see what this ratio was. And 2r equaled h. Okay, I'll divide the h, so it's like this. But then I'd have to divide the 2 on both sides. Yeah, okay? But anyway, here's the secret. R over h is 1/2, right? Or 2r equals h. Now what's volume of cone? 1/3
Pi r cube h,
pi r squared h.
r square, sorry.
Cool?
Do we have to memorize the formulas or will you give it to us?
Straw, good question. If I give you a cone problem on the test, I would give you the cone equation. But I would expect everyone to know area of a circle. Do you know that?
Yeah.
Pi r squared, good. Area of circle, circumference of circle, do you know that? 2 pi r.
No.
Know those, do you know volume of a box for this course? Volume of a rectangular prism.
Mhm.
Length times width times height, good. As long as you know those, you'll be fine, but if I give you cone, I would write that formula for you.
Okay.
Cool?
What about spheres?
Spheres, I would give you the formula as well. You know, I know I could sit here and go, memorize all those things, you know? You already gotta know all those trig derivatives and inverse trig derivatives and stuff.
Yeah.
But no, I'd give you sphere as well. All right. Here we go. Before I even start, before I even get to this, every time I'm doing a related rate problem with a cone, because there's a nice proportion here, I want to substitute something for r. So see that r there? I want to go over here and isolate r so I can substitute something. So what is r isolated? You can use this one or you can use this one, I don't care.
H over 2.
Is that right? So I'm gonna put that, highlight it, that's what I'm gonna use as substitute. R is equal to H over 2, circle it, you're coming up here, before I even start. So 1/3 pi times H over 2 times H. So it's a little different from our problem yesterday, but what's all that become?
1/3,
1/3, what's that 2 squared there becoming a denominator?
h over 4.
So I
H
get
squared over 4.
1/3 pi h squared over 4 times another h.
H, yep.
So it would be pi over pi h cubed over 12.
There you go, everyone. 1/12 pi h cubed, right?
Mhm.
And I'll take that 1 off there. I can just say pi over 12, huh? 1/12 pi, or how, pi over 12 h cubed, that's it. Now we'll crush this problem. There it is. I'm gonna write it again. Look, V is pi over 12 h cubed. Now we're rolling. Differentiate with respect to t. 3 comes in front. Decrease this by 1.
Mhm.
dh dt. Yeah. And it's plug time. Unless you want to simplify to 3/12. What's 3/12?
1/4.
And if you want to reduce that. Might as well. Then we'll plug. All right. They give us some numbers. Where's the 30 go? Here or here?
dv dt.
That's 30.
Mhm.
And it's positive, right?
Yep.
Pile is what? Piling up, right?
Mhm.
Volume was increasing in that pile. What's some ways to know that's 30 and not over there? I think that cubic off there. You know that's volume, right? That has to be the dv dt. Now, here's the question from the book. How fast is the height of the pile increasing when the pile is 10 feet high? Okay, put in a what? Well, how fast is that height increasing? $30 equals 100 pi over 4. How do you want to finish that?
So 120 divided by 100 pi.
That'll work. What would you do? Or question?
I have a question.
Sure.
I don't know how you got from V, that step where you got V equals pi over 12 H3 to the next one.
You got it. So once we got that volume formula in terms of just H. See, the other problems usually was just in terms of one variable. We were ready to roll at the beginning. Remember you actually have like the area of a circle? Pi r squared, just an r. We started right there. You always will differentiate. You always will differentiate both sides of the equation with respect to t. That's what you'll do. So you go, okay, that would become what? dv dt. But then when you differentiate this with respect to t, we're applying chain rule. Because that's not a t, right? That's an h. Well, just do the power rule. 3 pi 12 h to the second. And because a chain rule, the chain would be derivative of that letter with respect to t, and just apply dh dt. Cool. What was weird with this problem, the cone, is did we have to do a little weird work at first just to get it what? Nice and clean? It's the only problem you had to do that. The other ones start out right away, like tangent theorem, a squared plus b squared equals c squared, right? Or the area of the circle, things of that sort. Volume of the sphere, 4/3 pi r cubed, there's only an r on the other side of that equal sign. All right, that's 25 pi, and when you get dh dt equals 30 over 25 pi. Or, reduce it, 6 and the pi is in the denominator, what's the units?
Feet per minute.
Good job.
Where'd you get 25 pi from?
What I did was, I thought 100 over 4 is 25. Do some of these. I'll do another related rate. See, at this point, when we've done some great related rate problems, covered a bunch of triangles, a couple cones, we've done a circle, we've done a sphere, we've got that snowball melting. Cool. I say we look through here and pick one you want to do. Oh, they got a normal line in there.
Which number?
Number 6, see it? Remember the word normal line?
Mm-hmm.
You get this tangent line slope, what do you do with the slope? Flip the change sign. You know which one I think's the hardest? I thought, well, not the hard, I thought number 4 was tough. You want to do 4?
Okay.
Flip on the board. We gotta figure out whether something's true or false. Which one is it? Which one is what? True? All right, we gotta find a statement that's true. And all he did was give a little piecewise function. Four of these are false. One of them's true. let's try it out. Does anybody know about odd and even functions?
Yeah,
Odd functions, everyone have to be functions,
f minus x equals to f of x, right?
right? And they got symmetry with respect to the origin. Cool. Not any odd function has symmetry with respect to origin. Here's an image. Here's another image. The sine curve. How's the sine curve? Sine curve goes like this. The sine curve, y equals sine of x is an odd function. Just a couple examples. Odd functions. Cool. But this image, can we make a sketch of it? It's got the x cubed on this side, right? Well, what's this do on the right side of the piece? Now I noticed they're both connected at 0, and so it is a continuous graph. It is continuous, right? But I'm sorry, is that symmetrical with that?
No.
All right, A is out. Sorry, it's not an odd function. What's the letter B?
Is it discontinuous at?
That's false. They said it's discontinuous at 0. Everyone, it is continuous at 0. B's out. It's
Limit.
one of the remaining 3. C, the limit as x approaches 0 does not exist. False. The limit does exist. We can see it. Right? Left side of limit equals right side of limit. True? Right?
Mm-hmm.
Cool. That's not it.
F
Doesn't exist. It's either D or E. It's the true statement.
D is not true.
D says
prime of 0.
f prime of 0 equals 0. Now I'm going to put a question mark. We got to see if this is true or false.
This
That's
false.
probably the hardest part to this problem. You know what that means, everyone? We're looking at slope. And this is what we got to look at. Slope from left must be equal to 0. Slope from the right must be equal to 0. That must be happening, okay, for that to be true. All right, what is derivative from the left?
3x squared.
All right, so from left, everyone, slope, f prime, from left is 3x squared. Now you got to plug in the x value, which is what? X equals 0. What's the slope from the left?
0.
0, okay. And when that's slope from the what?
Left.
At x equals 0. Approaching from the left. What is the slope approaching from the right?
1.
Then that statement's false. And the slope from the right they're saying is a what? 1. You could probably see it in the image. Sorry. That's false. That's not true. That is not true. For that to be 0, both of them would have to be zeros. That's 1. So the answer has to be what letter?
E.
It's gotta be E. Let's see what they got for E. I haven't even read it. It's gotta be E. Gosh, they made us go through that whole thing to get the E. They said the slope is positive when x is not 0. Everyone look at our image. Is the slope positive?
Mm-hmm.
Yeah. Is the slope positive?
Mm-hmm.
No, so it's E. It's E. That's the true one. They're good though. They make you think. I like that. Not only do you do like, you get practice in this, you do some like, quotient rule and chain rule and stuff like that. Some of these make you kind of sit there and think.
Professor, if we do it like algebraically, like if for the odd function, if it like f of, I forgot, odd function is like f of negative x equals to negative f of x, right?
Yeah.
That's for the odd function, right?
That's exactly right.
Okay, okay.
And when he's talking about the definition of an odd function is really this. F of negative x must come out to be mathematically negative f of x. Right?
Uh-huh.
That's the definition of an odd function. You can do it that way.
Yeah, so if you do the one from the left, so f of negative x is negative x is x cubed, right?
Right.
And from the right, f of negative x is
Negative x.
So then both of them becomes odd function, but we have to do graphically then.
That's right. So I think what happens is we always got to look at the image.
Okay, yeah.
But you're right. You said separately they're both odd. But if you make it a piecewise, we have to look at the
Graph, yeah.
graph. Great point too. We're saying we can't rely on that definition when we do a piecewise. We're gonna have to look at the image. Make sure it has that symmetry.
Well, are you going to, I forgot all those algebra. Are you going to have this something like this
What's that?
in the exam? Because I want to look on the algebra. I forgot those algebra. Odd function, even function, symmetry to x.
Oh yeah, I wouldn't do that.
Okay.
The cool thing about even functions, though, everyone, when we get to area, a couple weeks from now, we do area under curves with the antiderivatives, is when it's even, you only have to do like half the graph because of symmetry, and you just multiply the answer by 2.
Can you graph that on a calculator?
You sure can. Show you how. You got TI-84?
T83.
That'll work. So he wants to know how can you sketch a piecewise on a calculator. All right. Sorry I didn't bring my overhead thing, but you don't need it. Ready? The key is, remember this for piecewise graphs on a calculator? Parentheses. That's the key. All right. So I'd have to go to my y equals, and I'm going to put x cubed inside a parentheses. And then right after this, I'm going to start another parentheses, and I have to write this. So I'll put the letter x, but then this symbol, I'll put it in yellow. I'm going to tell you where that's located on your calculator.
It's under test.
Oh, he knows. There's a menu called test. Is it the left column? Where's test? Off the math?
Second math, yes.
Second math, there's a menu called test, everyone, and you can actually get that symbol produced and then close out the parentheses. But look, I didn't put anything between these. I didn't put a comma or anything. I just went parentheses, parentheses. And then here, second one, do the same thing, x in a parentheses, and then x, grab that symbol, and then graph it. And it'll do it for you. It's kind of slow sometimes. It does one piece, and there's a delay, and then it does the other piece. But it'll do it. Graphing a piecewise. Hey, the only time I don't like it is when it gets to like 3 or 4 pieces. Then I notice it's,
Then it's confusing.
yeah, I don't like using the calculator. I'm like, I'll do it by hand. But when it's 2 pieces, way to go TI-8384. I mean, it does a really good job making both pieces. Cool. Hey, can we do another thinking problem?
Yeah.
All right. It's a challenging one, though. You'll get it. Anybody know how to solve a system of equations? I think I'll start with that, and then we'll do it. Anybody know how to solve something like this amount, like 2x plus y equals 4, and x minus 4y equals 8? I'm just making this up. Anybody know how to solve a system of
Yeah.
equations?
You have to multiply.
Substitution method?
You can
Anybody do the elimination method, or add out method?
Yeah.
Either of them work. Cool. So something like that pops up in this problem. I want to give you a heads up about it. It was buried at the end of this practice set. Way at the end. Look at number 25. I thought it was good, but it is. That's why I put it last, everyone. I'm like, ooh. Because of piecewise. We can't graph this yet, though, because they gave constants in it. And it goes, if g is differentiable of 3, what's k now? So you got to figure out k now, huh? Cool. All right. We know differentiable means slope from left must equal what?
Slope from right.
But you all agree? If a function's differentiable, it must be what?
Continuous.
Is lovely.
Continuous and must have a
So I
limit.
say we start with that. Let's start with continuous. If it's differentiable, it has to be continuous. So let's start with continuous. What would have to be true for continuous algebraic?
It has
To be
slope.
connected.
So let's start with that. I'll put continuous. Left side equation must equal right side, and plug in what for the x value?
3.
Brilliant. We'll start there, everyone. Take the top equation. This is number 25. Take the bottom equation. Let's plug in 3 for x and set them equal to each other. Okay? That's what would have to be true. To be connected, they both got to be in x equal to 3 be equal to each other. Okay. So I get k times square root of 3 plus 1 must be equal to m times 3 plus 2. Does that sound good?
Mm-hmm.
Does everyone agree with me? To be continuous, isn't that what has to be true? Continuous at 3, these two sides have to be the same y values. Right here, like, same y. Same y value at x equal to 3, that must be true. Now, we took care of that. Do you notice, everyone? You got an equation with 2 different variables up.
Mm-hmm.
So then we move on, we look at differentiability. To be differentiable, we know slope from left must equal slope from right. Okay. I'm gonna do the easy one. You gotta help me with the hard one. The slope from the right, when I saw it said mx plus 2. Do you agree the slope from the right is just m?
Slope
Does everyone
from-
agree?
Yeah,
Good.
m, yeah.
And the slope of this, and I'm like, But here's the hard one, you gotta help me out with this. What's the slope of that equation right there? So I need derivative of that. How do you get a derivative of square root of x plus 1?
Implicit
Power rule?
Product.
That k's a constant though.
Oh,
So we can carry the constant.
so it's gonna be.
So we don't need product rule, right? Some of you might be like, oh, it's two different variables, but that k is just a
So
what?
it's just a power rule.
Just a constant. So we can just do power rule.
Uh-huh.
So we can look at this as k times a parenthesis x plus 1 to the
half.
half. All right, I want to do the differentiation. Just let that k hang out in front, okay?
Uh-huh.
We don't need product rule. Just, Josephine.
Slope from the right,
Slope from the right. You remember mx plus b? M is slope.
is that it?
Another way to do it though is, Josephine, think of anything like that. What would be the derivative of 3x plus 5 if you did derivative? Differentiation, wouldn't derivative be 3? Good. Or I'm gonna do it on 2x minus 1, derivative is 2, 5x plus 4, derivative is 5. That's another way to look at it. You can go, oh, m is the number in front of the x, so it would just be the m. Cool? So I want to differentiate that. What do you get? Let that k just hang up front.
So would you,
Half a k, decrease it by what?
1.
But I don't like how I wrote that. How could you write that better?
Divided by, like, the square root of k of x plus 1.
Good call, I'm gonna do that. All right. Oh, cool. So everyone, the hard work's done. I was just wondering if you had any idea how we could solve this system now. We got a system of two equations. I heard words like substitution. We just gotta solve
you
that
can
system.
multiply by k to get rid of the fraction?
No, so m is equals to that. So you take the k and multiply by 3 plus 2, and then you
Put
can
it
do
right
it.
there?
Yep.
I like that
Got
idea.
it?
What do you think about that, Amber? How
Wait,
about
what?
substitution?
I lost you.
Hey, how about the substitution method? Do you agree?
Yeah.
You go, all right, we got our system of equations, true? We got this one from this side, we got that one from that side. And we're saying, well, if that's m, we could take this and substitute it into this equation for the letter m.
Oh, okay, yeah.
So what would that become? I'll just draw an arrow. And so after substitution, I'll put it in yellow, I get k times square root of, what's square root of 3 plus 1?
2.
Are you okay if I write that as 2k?
Mm-hmm.
Is that 2k? Square root of 4?
Oh,
Wait, are we plugging in the k as well?
You agree that that's 2k? Square root of 3 plus 1 is square root of 4? And square root of 4 times k is 2 times k.
Wait, we're plugging in this entire.
I haven't done it yet though, just, I'm cleaning up that left side. Isn't that number right there 2?
Okay.
3 plus 1.
Yeah, 4.
Oh good, square root of 4 is what? 2? But rather than saying k2, I could say what?
Okay.
Okay.
Just try it a little bit better. So now I get 2k equals 3 times, we're gonna put something in place at m plus a 2. And let's bring it in here, what's going in here? Substitution. K over. And what am I plugging in for this x right here? Oh, there's an x here, what could I plug in
3.
here?
3.
You bet, everyone, let's plug in x equal to 3. Remember this was about going on at 3?
Do you plug in 3 2 times?
What's that?
You already plugged in 3 with the mx plus 2. So you plug it in again when you substitute m?
This was the 3 from that side, and we have to plug it in again over here, you're right. Unless it was at x equal to 7, you'd plug it in x equals 7. So what's all that become?
So it becomes 2k equals to 3k over 4, 3k over 4 plus 2.
How much you need to solve for k here?
Yes, we can.
Get it right here. I went 2k equals 3k over 4 plus 2. Remember okay there?
Uh-huh.
I want to make sure I didn't get ahead of you. Going all right to that point?
Yeah.
Cool. And now I know you can solve that thing. How we solve that? Want to collect your k's on one side? What's 2k minus 3/4 k? And like 2x minus 3/4 x. Yeah, it's 1 1/4 x, right?
Yeah.
What's that, 5/4?
Yep.
And isolate k. Multiply 4 on both sides.
8.
Divide by 5. Hey. I mean, that problem wasn't bad except for one thing, solve a system of what, equations?
Mm-hmm.
That's what I mean. That's why I wanted to say, that's what made that problem challenging. That's why I put it like that.
So m should be like 8/5 over 2.
Oh, good. How are you going to get m now?
Put the
You
k.
have to put it back in. You go where? And you can look at your work. Go, where can I find something equal to m? You might use it here. Look at that one. You got 2k equals 3m. You can use that one. Right? Anything you found easy to solve for your m on the board. I like this one. So 2k equals 3m plus 2.
Now we know what K is.
Now you know what k is. We can just put it right in there and get that m. Right?
Mm-hmm.
So
250.
I'll just go over here. 2k equals 3m plus 2. Times 8/5. 16/5. All right, what's 16/5 minus 2?
6/5.
And when you divide it through,
250.
2/5. Got it. Woohoo! Syrah can all that junk.
Yeah.
I love it. It just makes you think. You think about, gotta be continuous. Slope from approaching from the left, maybe you could slope approaching from the right. Oh, but we got a system of equations here.
Wait, after you got the k equals 8 over 5, then...
Then I looked for something easy on the board that had an equation with k and m in it that I could substitute in it. I like this one. 2k equal to what? 3m plus 2. And I took that 8/5 k,
And plugged it in.
for k. And then I had to solve them. You got some fractions there, but wasn't as bad as you think. Yeah.
Now on number 23, what are they asking for?
Let's look at that. A mass on a spring vibrates horizontally on a smooth level surface. Okay. Its velocity at time t is given by, let me write this down, what does it say?
dt equals to negative t cosine t.
Alright, on. That's velocity. During what time intervals between time equal to 0 seconds and time equal to 6 seconds is the mass moving to the what?
Left.
Left. I said note, a calculator is not necessary, but if you use it, just make sure you put all your answers right, it's accurate to at least 3 decimal places. So we're going to talk about different ways to approach this. And here's velocity. The question is, you got to get the interval. When was this thing moving to the what?
Left.
Moving to the left. Is velocity positive or negative? Negative. Outstanding. So in answer to this question, we just got to see when the velocity is negative. There's velocity between what time? 0 seconds and 6 seconds. Does everyone agree?
Yeah.
So there's our problem solving approach. We got to figure out when was the object moving to the left. We said that's when velocity is negative. They said only consider 0 to 6 seconds So we're just gonna look to see when is the velocity negative between t equals 0 and t equals 6. Now to do this, one way, you could graph it on your what?
Calculator.
Calculator, if you want. Now if you're like, is there a way to do this without the calculator? Yeah, you just gotta know your trig and your, all students take crack stuff and all that junk, you know what I mean? ASTC and what's sign positive, when's sign negative, you know what I'm talking about? Through the 4 quadrants. So we can do it. Which way would you like to do it? Both?
Yeah.
All right, let's start with the calculator. Does the calculator make a decent graph? You gotta just go from 0 to 6 on your window. I don't know what that graph looks like, so you have to know. And I'll talk about how you can do it without a calculator.
So x max is 6.
I like it, X max 6. And I'll come look at people's calculators. I'll make the sketch here. Here, lead. We're just seeing when the velocity, when it's underneath. And we'll play. Now, what mode you gotta be in? Degree or radian?
Radian.
And when check your mode, make sure it says radian. Radian mode. Is it working? You in rad mode? Look at mode.
I'm in right now.
So you're in radian mode. Did you make the window 0 to 6? Cool, I'll go with yours. I'll put it on the board too.
Like,
Ooh, that's nice. It went a little there. So it looks like we're gonna have to write from here to here and then again from there to there, right? Now how can I trace there? Trace to that, do you know how to do the 0 thing? Or when you're there, second calc. Oh, that's smart. We can just do intersect. Better, man. It's quicker. You run around. If it shoots over here, we'll just put the curve. Yeah, it gets close. All right, now we're looking at the graph. I'll make the picture on the board. What do we get? We get that 1.57. And when the graph went like this, so we can see, this is 6 seconds, we graphed it on a calculator. It's from here to here, but then we're gonna have to say union from there to there, okay? I'll shade in. And we're gonna say from here to here, and then again from here to here, because that's when the velocity was underneath, true?
Mhm.
Now, we just did the intersect button with, you could do 0, 0 if you want, we used our calculator. We noticed that number right there was 1.57. Okay? Now, I was wondering if someone wants to use intersect to get that button. That died.
4.71.
4.71. And so how can I write my interval? From 0 to what?
1.57
Union?
4 point whatever to infinity. 6.
Good. I want to cover that. Now, if you're like, hey, can I do this without the calculator? Yep. I'll show you how. Everyone know ASTC? All students what?
Take crack.
Take crack? No one know that? I'll show you. But I want to make sure, Josephine, you're okay with that? That whole hand, there's the graph. We're like, oh, yep, from there to there, from there to there, it's moving to the left.
what's this?
Didn't work?
In the middle?
Radian mode?
No, what's?
You know how to use intersect? Let's see. Oh! Negative x, you don't have to put that piecewise part. That's why, so you can just go up here. Just go over here and just delete all those. Yep. Then you do graph. It goes too far, we'll just take the window and go from 0 to 6. That's what we'll do. Well, that's a cool looking graph. Let's just go from 0 to 6. Hey, you can always fix the window, do zoom 6 to put it back to normal. But now you're not, all right, and then we're gonna trace. Do you like intersect or 0? So if I just trace, I'm gonna trace here. I just wanna know that number. One of them's called second calc 0. I have to left bound.
How do you find the intercept? Do you remember about that?
Right bound to the right of that.
It's second trace
And
and
then
then 5.
No.
You do the same
The
thing.
intersect at the point. Like remember x equals to 0? How do you do that? Do you remember that?
It's, you keep pressing the enter and it gives you 2 coordinates for x and y.
Second trace.
Yeah, and then 5.
Did it work?
And then keep pressing on the enter until it gives you X and Y.
Second trig. Oh, intersection 5. Then 5.
Hey everyone,
It should give you something like this.
what's the phrase?
Give all.
0, 0.
All students take what?
Not the graph.
Take correct? Hey, was there another way to this problem? Yeah, first of all, they said time had to be positive, right?
Yeah.
So do you agree with me? I can always assume that this t here has to be positive. Someone follow me? Good, so t's positive. Now it says negative cosine. I just gotta know where's cosine and what's going on here. So if it's a negative in front, you agree, because all trig functions are positive here. But it's already got a negative here. So you agree that means from here to this number, because it's already got a negative, it would be negative, right? But then, isn't cosine negative over here?
So it should be positive.
Isn't cosine negative here? So what would be a negative times a negative, starting right here?
Positive.
Positive, so it'd be positive from here to here. Isn't cosine negative here? Cosine's negative here, and a negative times a negative would be positive. It'd stay positive from here to here to here to here, here, and then again here, because cosine's positive here, this velocity would be what, starting at this value?
Negative.
It'd be negative again. So another way I could have written this answer, if you use that, union,
3 pi over 2 through 6. Hold on a second. 0. Oh, why it is positive you're asking for.
Yep. Isn't that neat?
Uh-huh.
I just wanted to show it to you. You go, oh yeah, I know these. I know these numbers. I know ASTC. I know when things are positive and negative for cosine. Cool. Awesome. Any others on here? Or any topic you want to review? Chain rule?
You wanna go over the chain rule?
I'll find one. You want a chain rule? I'll find one on here. You got one?
Related rates.
Oh, you want another related rates?
Can you do the cone?
Now, do you want a cone? You want a triangle? You want
Can you do the cone one on there?
on here?
Yeah, the one with the h minus 5.
Let's do it. We found another cone. We'll do that. You got one? Oh yeah. You sure can.
Can we get a circle one too?
Oh, I'll give you a circle. If it's not on here, they're easy to make. You'll find circles easy because just like area, pi r squared. I think there is a circle on there. We're gonna do the cone one. Look at number 20. See it? Let's do the cone one, then we'll do 20. Does that sound good? Hey, before I do that though, what's the area of a circle? Pi r squared. What's the circumference of a circle? 2 pi r. All right. But we're going to do this cone one. Which problem is the cone one? Which one was it?
I think it's 24.
24. And when this is our typical cone problem, just like the other one, but there was something funny about this problem, how it did a h minus what?
12.
It kind of throws you off.
Yeah.
It throws you off. Always one little thing, you go, what the heck's this h minus 12 thing? So let's read through it. They go, water is draining from a conical tank with height 12 feet and diameter 8. Okay, so we're going to draw a conical tank. And here, just let it drain here. Water's draining. Here's your cone. Height's 12 feet. 12. Not drawing a scale there, right? That's 12 feet. Diameter is 8. Anybody know the radius?
4.
Is you okay if I just put 4 of them? I want to make sure everyone's okay with that. Are you okay if I just go right to radius? They said diameter 8, I'm going to make R4. Is everyone okay with that? The reason is I always want to look at the RH relationship. We all know I'm eventually getting to this. We all know I'm eventually getting to this. And so that would be given to you, right? I'd give you that form, but eventually we're getting there. So when they said diameter is 8, I'm just making R what?
4.
By the way, does anybody know what the ratio of R over H already is?
1/3.
One
What
One
is
third.
half.
Is it 1/2?
It's 1/3.
1/3.
Because it's 4 to a what?
4
12.
over 12.
So if you solve for R, what would R equal?
H over 3.
So that's equal to 1/3.
Can't you just memorize that?
Remember last problem though, it was H over 2? Do you remember? It wasn't H over 3 last time.
How did you?
Do you remember? So that's what I mean, it depends on the way they set up those dimensions on that cone. So that's why we can't always say, like last time, it was a ratio radius equal to height over 2. Because they said something about the diameter or height were always the same size. Cool. But now I'm just gonna substitute this where?
For R.
Alright, what do you get?
1/3 pi h over 3 square times h.
So it'd be pi h cubed over 27.
Pi h cubed over 3 squared is 9. 9 times 3 is?
27.
I don't want to rush anybody, I want to write this again. But that's why we couldn't just memorize that, because it depends on the relationship between R and H.
Can you go between the first, from plugging it into that?
You bet.
Step by step?
You bet. So what I did was, first of all, you saw I put H over 3 there, right? So now, mathematically, let's start by squaring both of those. You would get 1/3 pi h squared over 3 squared. But I know you know 3 squared is 9, right? Cool. So now we have this. So we got that step. But now you have a 9 and a 3 in the denominator. So in our next step, let's multiply the 9 times the 3. That makes 27. And then h squared times h is h cubed. So we finally got V. Hey, you remember what we always do next after this? Because I remember you asked what we do. Differentiate both sides with respect to t. So this will become a
dv dt.
dv dt. And here we do let's do a power rule on that. And then write dh dt, right?
Mm-hmm.
3 goes in front. With that constant, decrease it by
dh 2 1, yeah.
Times dh over dt.
I want to rush this, I want to wait till everyone gets caught up, because some of you may reduce that ratio there. Anybody want to do something with 3/27?
Yes, pi
Over
over
9.
9 h square.
Just pi square root of 9.
So pi h squared over 9. Pi 9 h squared dt.
I put the 2 in front.
And we are ready to plug stuff in, right?
Mm-hmm.
Amber, you okay with this?
Yeah.
Yeah? All right, let's see what they got. Let's see what, we're gonna plug stuff in. Usually at this point, everyone, they said, this is 20, this is 10, right? At this moment. Let's see what they got. So we go to this problem and they said this. The depth h in feet of the water in a conical tank is changing at the rate of h minus 12 feet per minute. Okay, let me say that again. The depth h in feet of the water in a conical tank is changing at the rate, that's a rate of change.
Mm-hmm.
They're saying the rate of change of the height with respect to time is h minus 12.
So does
I can replace something in that equation with an h minus 12.
dh dt.
Which one, from there to there, to there to there, something represents, let me read it to you again. The water in the conical is changing, here it comes, changing at the rate of h minus 12 feet per minute. And they said that's the depth
Height
changing,
and-
the height is
height.
changing.
Height and
So dh
Exactly.
dt.
the DHD2.
Brilliant. Does everyone see that? I can read it one more time, Josephine, if you want me to say. We can replace, in this problem here, dh dt with an h minus 12. Because they said this, the depth h is changing at the rate h minus 12. That's the rate of change of h. So I can just replace this thing right here with h minus 12. I have to admit though, we never saw any problem like that, did we, Bill Rash? Usually it was like, usually they just said it was like 4 or something, right? 4 feet per minute or 4 feet per second, true? 4 inches per second, all that stuff, but we'll put that there. And then this is what, h squared?
Yep.
That's
3.
a pi over 9.
Pretty square.
So negative.
Oh, did they give us a measurement?
H is 9. 3.
And you said plug it in, that was good. Because then at the very, very end, they go, when h is 3.
So negative 9 pi.
What's all that math?
Negative 9 pi.
Because that's negative 9. I got you. Negative 9 over 9 is negative 1.
Times 3 squared.
And that's a 9. And when, look at the image, they said the water was draining.
So
So
it's
does this seem like a typical answer that it's
Yep.
negative?
Because it's decreasing.
Nice. What's the units? Because it is a dVdt.
So that's
I'm loving it. And was it feet?
feet, yeah, feet. Cube, feet
And
cube.
they're cubing this because this was rate of change of a what?
Volume.
Why is it negative?
And why is it negative? We saw this 3 minus 12 turn into what? Negative 9. But when that happens, what we should do, Amber? We should look back at our image and see if this seems right. Why are we getting a negative rate here? Oh yeah, water was what?
Draining.
It was like this, then it was like, then it was here, then it was here. The volume was what? Decreasing in that cone. Cool? Good. That was a good one. Hey, you said the circle, right? Well, that's a lot easier than this one because it starts out with just what?
Pi squared.
What's area?
Pi squared.
Is it just feet cubed or is it feet cubed per second?
Oh, thank you so much. This was a rate of change. What was it? Was it seconds?
Minutes.
Minutes. It was minutes. So Josephine, thanks. It is a rate, so it's got to be feet, cubic feet per something. In this case, it was minutes. We'll put per minute. Thank you. Hey, so where was that circle one? 20. Hey, this will be our last one, and if you want to stick around more, we can. And then don't forget, Monday's gonna be a what? Review day. So if someone didn't come Monday, I'm not gonna be like, hey, where were you, screaming at you and stuff? Because you might be one who likes to study on your own, you know? Because they'll just be reviewing, just getting any questions you want. It could be anything from chain rule to power rule to product rule to related rates to, what else do we do? Velocity, position, acceleration. Our last one, and when radius circle is decreasing at a constant rate of 0.1 centimeters per second. So I'm thinking, I'm just gonna draw an image here. We got a circle, and is it increasing or decreasing in size?
Decreasing.
It's doing this, huh? Right? And how fast was it decreasing? The radius was decreasing at what rate?
0.1 centimeter per
So
second.
can I say this?
It's gonna be negative.
dr dt equals, what's that number?
Negative 0.1 centimeter per second.
I'm gonna make it negative because decreasing, good.
What number is that?
Is that what I got with that?
Yes.
Oh, this is number 20. I'm sorry, Amber. But hey, I read the first sentence, Amber, I'm sorry, and you go, the radius of a circle is decreasing at a constant rate of 0.1 centimeters per second. So, decreasing, I'll make it negative. They said radius decreasing, so I'm gonna say dr dt and just make a note of that, right?
Okay, yeah.
And then it was centimeters per what?
Second.
What is the rate of change of the area? Now, everyone, this in terms of C thing may throw you off. We're going to ignore that for now. Let's key in on what's important. We got to find what is the rate of change of the area. So here it is. I'll get all that volume junk out of the way. Get that out of the way. All right. Here we go. We're going to differentiate this, right? All right, dA to
dt.
dt. Now do a power rule on this with the chain rule.
2 pi r dr dt.
So already I can substitute what number there?
Negative
Negative
0.1.
And then someone in here is gonna help me out with this answer, because I was confused about this big C thing. And you're gonna help me out. So this is what I have, except you're telling me right now I can put a negative
0.1.
0.1 there.
Uh-huh.
But I'm really, you're gonna help me out, I'm thrown off by this thing about a big C, circumference C, and I gotta write the answer in
So
terms of
C equals to
C.
2 pi r. So C times,
Who else saw this? Oh, you all are good. Who saw this? Circumference is what? 2 pi r. So Sarah, remember I said it earlier, I said, I want you to all know area of a circle, pi r squared. I also want you to know circumference of a circle, 2 pi r. And throughout this course, we'll probably see a lot of boxes or rectangular prisms. Volume is length, width, height. But when it comes to volume of a sphere, volume of a cone, I would give you those.
So the derivative of the area of the circle is the circumference.
That's right. Because the derivative of the area of a circle is circumference. But Evan, you're saying I could replace all these three things right here with a big C. Everyone agree? Because that's C, isn't it? That's circumference. So I can replace this, substitute a big old what?
C.
And I hope I can find the right answer in that multiple choice selection.
C for calculus.
C for calculus. And when is one of those answers this? Which one is it?
B.
Everyone, great job, great job. Stick around, you get more questions. Monday we'll review, but if you want me to do more, I mean, stick around. Monday review, anything, chain rule, what else? I'll be honest, you could have taken a test Monday, I knew that ahead of time. I always know we have an extra day in there where I can put it here, I go, should I do a test 3 or test? I always do it on test 2 because of chain rule. You know, I always want to make sure I get every chain rule answer. Because as long as you get chain rule down, Calc 2 and Calc 3, no problem at all. If someone misses that rule, those courses can be vicious, right? Because they'll continually miss chain rule. So, we'll have a great weekend.
Are you gonna have the,
Solutions?
no, the equation?